The overall purpose of this experiment was to observe an object that was traveling with a velocity that was not constant, meaning that the object's speed was increasing or decreasing over a period of time while also traveling in the same direction. One of the main goals was to know the weight force and the drag force acting on the system and account for those forces in a computational model. Newton's second law was used to explain the motion of the observed object as well as to produce the computational model, which predicted the position of the object. The original model that was produced only accounted for the weight force acting on the object and underpredicted the position of the object over time. The model was adjusted to account for drag force, in which case the model was unable to more accurately predict the motion of the system than when considering weight force alone. I believe the position was underpredicted because the mass of the model may have been too great for a drag force to have any substantial effect on the object, and it is possible that I myself may have exerted some force on the object upon releasing it at the beginning of the trial. I began my experiment by recording a pair of socks being dropped from approximately 1.5 meters above the ground. In this video, the pair of socks is the system. The red dots indicate the position of the center of the pair of socks in each frame of the video clip. And since the camera used was set to record at 30 frames per second, the change in time between each frame is 1/30th of a second. You can see in the graph that the slope of the line is curved, indicating that the velocity of the pair of socks increased as it descended towards the floor. Since the velocity of the pair of socks is not constant, this must mean that some force or forces are acting on the system to add up to a non-zero net force. The first model that was designed considered the weight force to be the only significant force acting on the falling socks to determine its velocity, meaning our net force would be equal to the weight force, which is equal to negative mass of the socks times constant g times j hat. Earlier in the code, the mass of the socks was set equal to 0.2 kilograms, which is a rough estimation of the mass of a typical pair of socks. G, a known constant, was defined as being equal to 9.8 meters per second squared, and j hat was defined as being equal to a unit vector on the y-axis. Here, Newton's second law is integrated into the code so as to predict the velocity of the falling socks. Once the velocity of the socks has been calculated, this value can be used here to predict the position of the socks. This model was set to run for 0.533 seconds, the same duration of the observed trial. When this model is run, the motion it predicts is roughly equivalent to the falling motion observed by the socks. Negative direction along the y-axis, and the direction of the drag force will always be acting opposite the direction of motion. In this version of the model, the net force was set equivalent to the weight force plus the drag force. Here, drag force was set equal to b times the magnitude of the velocity squared times positive j hat. B is a constant that was defined earlier in the code, and that depends on the system in question. Therefore, a little guesswork had to be done to determine an appropriate value for b. I chose to set b equal to 1 times 10 to the negative 10th power. When this model is run, you can see a yellow arrow, which is a visual depiction of the vector representing the weight force acting on the system. Another blue arrow was also encoded into the model to depict the vector representing the drag force on the system. The amount of drag acting on the model system is so small that the blue arrow is not visible, but if the drag force was more prominent, the vector would be pointing upwards towards the point where motion began. By taking a closer look at the data obtained by this model and comparing it to the model considering only the weight force, we can see that the model including drag force underpredicts the motion of the system just as much as the original model did. Enough for drag force to not have an effect. Because neither of these models accurately predicted the motion and therefore did not accurately predict the terminal velocity of the falling socks, you can assume that there are most likely other forces acting on the system causing it to move as it did. If we go back and look at the video, my hand seems to flick as a pair of socks is released, unintentionally adding force to the system. So what if the socks actually were pushed downward instead of being dropped from rest? In terms of terminal velocity, the socks would reach the same terminal velocity as they did when they were simply dropped from rest. However, they would reach this terminal velocity at a quicker rate. We can examine this concept by modifying the computational model time to 1 second and compare this data to that of the data collected with an initial velocity of 0 meters per second. We can see that very early on, the model system with a non-zero initial velocity is accelerating quicker than the model system with an initial velocity of 0, and that the slope of the non-zero initial velocity system becomes straight at an earlier time, which is depicting that the system is reaching terminal velocity at an earlier time when it starts off with a velocity that is not 0.